To finish up, we're going to look at the rectangle intersection problem. It's got important practical applications and uses the techniques that we've been studying so far. And it's a simple generalization of our line intersection problem. So now we have a bunch of rectangles. They're all oriented horizontal or vertical. And what we need to do is find all the intersections in that set of rectangles. And again, n could be huge in applications, as we'll talk about in a second. And the naive brute force algorithm involves checking each pair of rectangles for intersections. And what we want is a more efficient algorithm than that, as usual. And again, to keep the code simple, we're going to assume that all the coordinates are distinct. We don't have any equal lines we have to worry about. Whether we consider rectangles that touch to be intersecting and so forth. So that's the problem, rectangle intersection search. And this is historically an extremely important problem. In the 1970s, when we switched to very large-scale integration for computers, we were switching from a situation where we were wiring physical devices together to a situation where we were essentially drawing the computer. And there were machines that would take drawings and return, and from those drawings, like this, make physical things that implemented computers with different layers and different physical materials interacting in different ways. Some things are wires, and some things are switches that are used to implement memory bits in computer logic. But the key point about it is that designing a computer became a geometric problem. And so people, to design new computers, would make huge drawings that just showed the lines that corresponded to the materials that had to be created to make the computer. Now, it was very expensive. You didn't want to have any bugs when you're making a chip. And there were various rules about what you can do on these drawings. And basically, these rules had to do with doing this orthogonal rectangle intersection search. You can't have lines that come too close to other lines. Certain types of lines can't intersect. Need spacing between certain types of wires. And you wanted to, before you tried to make the physical circuit, to do this checking, which involved this orthogonal rectangle intersection search. And it was actually the case that the progress of faster and faster processors with more and more components was slowed because people were using the naive quadratic algorithm to do this design rule checking. And it's an example of Moore's law. So as we built a faster computer, say in 1970X, we needed to check in rectangles. But now, maybe a year and a half later, you have a computer that's 2 times faster, but you also want to build a bigger computer so you have twice as many rectangles to check. So you have 2n rectangles to check now, and your computer's twice as fast. So we get to use the faster and bigger computer to build faster and bigger circuits, but that doesn't help if you're using a quadratic algorithm. If you're using a quadratic algorithm and it takes you m days to check your design rules, and people were running these things on the order of days, then for the next computer it would take 2m days. It would take twice as long. And so people that were using quadratic algorithms were definitely held back. And it was Ed McCreight at Xerox PARC who discovered interval search trees and the logarithmic algorithm that allowed us to sustain Moore's law and keep building bigger and bigger computers by changing this quadratic algorithm to a linear arithmetic algorithm. And let's see how it works. Really, it's a modification of the sweep-line algorithm that we looked at for intersecting lines, but now we're going to use that for intersecting rectangles. Rather than using range search as our basic operation, we're going to use interval search. So now, every time the line sweep hits a rectangle, that corresponds to an interval. If it's the left part of a rectangle, then we put that interval into our interval search tree. So in this case, we put on 0, and then we put on 1, and then we put on 2. And that'll give us now 3 rectangles on our sweep line. And so now the question is, when we hit a new rectangle, we want to do an interval search if we're at the left, to check which ones intersect. And the interval search tree algorithm is going to tell us which intersections there are right away. When we reach the right, then we remove integrals and so forth. But with the basic interval search tree algorithm and the sweep line process that we've talked about, you can get the orthogonal rectangle intersection search problem solved in time proportional to n log n plus r log n, where r is the number of intersections. And typically in design rule checking, you wouldn't expect too many intersections. So again, just as with line intersection search, using a priority queue or a sort is only n log n for processing the x coordinates. And because interval search trees take log n for every operation, the insert and delete intervals is n log n total, and the searches is n log n plus r log n. So the bottom line is that the sweep line algorithm takes this rectangle intersection problem and reduces it to 1D interval search, and we have an efficient algorithm for that problem, and that enables us to solve the problem in linear rhythmic time instead of quadratic time, and that definitely enabled new progress in technology, and it's a fine example of the importance of algorithmic technology. So here's our summary of applications of binary search trees for geometric problems. We started with one-dimensional range search and just used a regular binary search tree to compute ranks to get the answer. But that, as the basis, we were able to solve the two-dimensional line segment intersection search using the sweep line algorithm. Then we looked at range search and other operations using KD trees. Again, modification of binary search trees. And then the interval search tree to solve the one-dimensional interval search problem, and then how that corresponds to the basic algorithm that you get to if you use the sweep line algorithm to solve rectangle intersection. Many of these problems are the basis for geometric processing of huge amounts of data that we see all over the web. And our basic search tree mentality and APIs and binary search tree data structure give us efficient solutions to these important practical problems.